All right, so this is the first of 2 lessons looking at evaluating limits in various ways that are algebraic, not just by either purely by looking at a graph, although we will get to that for the first question, but mainly not just by substitution, which is what we kind of saw last day. If we didn't have a graph, we were substituting values in, and getting that gave us a good sense, but didn't really prove anything. It just gave us a good sense, an educated guess about what various limits were. First, I want to mention some of these properties of limits, and I want to say this quite quickly. So in general, if you are finding the limit of, you can think of it as 2 functions, 2 terms, whatever, adding or subtracting, or finding the limit of all of this. If you want, you can find the limit of each of those separately, and then add or subtract them together. If you're finding the limit of some function that's being multiplied by some constant, if you want, you can kind of imagine the constant being factored out, focus on the limit of just that function, and then multiply by the constant. If you're finding the limit of 2 functions being multiplied to each other, what's always correct is to find the limit of each of those functions separately and then multiply those limits together. If you're same thing with dividing, if you find the limit of a quotient where you're dividing 2 functions, if you want, you can find the limit of the numerator and the denominator separately and then divide those answers as long as your denominator does not approach 0. If it does, then you're dividing by 0, and that doesn't tell you, you can't determine the limit from that. And lastly, if you have a limit all being raised to some power, if you want, you can find the limit of just the function, and then afterwards raise that to the power. All right, so a lot of these are things you'd probably assume would be true anyways. Let's use some of these. And first, again, and the only question today where I'm going to be looking at a graph. What I have are 2 functions here. F of x is this sort of 2 line segments, and f of g is this blue rational looking curve. So I want to find the limit as x approaches -3 of f of x plus g of x. So one thing I can do, if I look at this, is I can look at these 2 parts separately, and I can try to find the limit as x approaches -3 of f of x, and separately find the limit as x approaches -3 of g of x, and then add those 2 things together separately. And so both of these I can probably evaluate by just looking at the graph. The limit of f as we approach -3, that's looking right here. So I can see that's at -1.5. So -1.5, that's the limit as we approach -3 of f of x. For g of x, we approach -3. -3, that's right here. That's at -3. And so the limit of g of x as we approach -3 is -3. Or I shall put plus -3. You know it's the same thing. And so now I can just add these together, and I get -4.5 or -9/2. So that there is the same as the limit of all of this right here. Okay, next, the limit as x approaches 6 of f of x, but the square root of fx, I should say. Well, as we saw before, if I want, I can focus on just the limit as x approaches 6 of f of x, and then square root that. So let's look at the f of x as x approaches 6. As x approaches 6, I'm right here, and I can see the limit as x approaches 6 is 4. So then I'm going to have the square root of 4, which is 2. And finally, the limit as x approaches -2 from the left, are f of x times g of x. So let me look at each of these separately. Let me think of this as the limit as x approaches -2 from the left of just f of x. And then I'm going to multiply that by the limit as x approaches -2 from the left of g of x. Let's focus on that part. So the limit as x approaches -2 from the left of f of x. Well, that's where it approaches -2. So from the left, same thing as from the right, it's -1. Okay. What about the limit as we approach g of x from the left at -2? Well, g of x has an asymptote at -2. So as we approach -2 from the left, it's going down forever. So the limit of g of x as we approach -2 from the left is -infinity. So what does this limit equal? I have negative 1 times negative infinity. Well, keep in mind, negative infinity is not actually a number. The key is I have a negative times a negative. And so I can see the limit as we approach negative 2 from the left must be positive infinity. Which means, another way of looking at it, if I found the equation for f of x and multiplied that function by the equation for g of x, there would be a vertical asymptote at when x is negative 2, and from the left, the curve would actually be going up. That's it. I didn't actually have to graph anything, just by looking at these limits kind of separately. OK, so essentially I used a number of these properties we saw here of limits. All right, that's it. Algebraically, how can I find some limits without just substituting values in? Well, there's nothing wrong with substituting values in. I always encourage you to see if it's going to work. For example, for this limit right here, the limit of this expression as x approaches 1. Again, notice if I just replace x with 1, in this case, it's great because I just get 1 over 2 plus 1 minus 1/2 over 1. And again, all I really care about when evaluating these things is that I'm not dividing by 0. And if I can see here, I'm never dividing by 0. So there's nothing wrong with substituting a value in. It's just usually not going to be helpful, as we'll see for every other example after this. But it's not a bad idea. In this case, I substitute exactly 1, not 0.99 and 1.01. I'm literally just substituting 1 in. And so what do I get here? I get 1/3 minus 1/2 over 1. Well, I don't need to show divided by 1 anymore. 1/3 take away 1/2 is a 1/6. So the limit as x approaches 1 for all of this is a 1/6. Sorry, negative a 1/6. My bad. 1/2 is bigger than 1/3. That said, the reason this was so quick and easy is because this function was this expression right here was defined when x equals 1. I'll probably never ask you a question like that again, because honestly, that's not really the difficult part. The difficult part is something like this, the exact same expression, but now as x approaches 0. So I can just see right away, if I replace x with 0, I'm dividing by 0 here. And so this does me no good. In fact, if you actually do that, you may think the limit does not exist or something. And that might be the case. I just don't know that yet. Just about every single time you're going to evaluate a limit, you're going to get division by 0 in the denominator. The question is there something else going on there that we can't see? So for this, I don't want to just substitute x with 0. It does me no good. So what can I do? Well, let's algebraically see if there's a way to simplify this expression. And so let's take my numerator and find a common denominator, which means really I'm going to multiply this side by 2 plus x, the numerator and the denominator, and this side by just 2. So finding a common denominator. So I have 2 minus 2 plus x over 2 times 2 plus x. That's it. All that's being divided by x. I'm going to write it as times 1 over x. Same thing. The whole point is, once I realize I can't just substitute x with 0 and get a value, if the limit is going to exist, I have to be able to, it must simplify down to something in which eventually I can just replace x with 0. If it doesn't simplify down to something else, or if I can't write it in an equivalent form in which I can just substitute x with 0, only then can I say that limit does not exist. But notice if I clean this up a bit, in my numerator, I get just x over 2 times 2x times 2 plus x. Right, if I distribute the negative here, my 2's cancel out. My x's, it should be negative x in my numerator. And my denominator, again, x times 2 plus x. Well, at this point, my x's cancel out. And so this messy expression, I can now write as negative 1 over 2 times 2 plus x. Notice at this point, I can now substitute x with 0, and I'm not dividing by 0. I algebraically found an equivalent expression for this expression right here, and I got to here. So these two are algebraically equivalent, but this expression here, I can replace x with 0. And so which means I can evaluate this limit directly without having to look at a graph or substitute values that are close to 0. And so now at this point, I'm actually going to evaluate my limit. I'm going to write the limit as x approaches 0, because now I can actually evaluate this. And I'm literally going to go to my equation and just write that x as a 0. which again, I tried right away, didn't do me any good. Now it does me good. I get negative 1/4, and that's my limit. And this idea of taking a limit and checking if I can just substitute the value in right away, it's almost never going to work. And then realizing, okay, that doesn't actually tell me much of anything. But then realizing, okay, there's got to be some sort of algebraic work I could do to find an equivalent expression. In this case, I think it's safe to say this is simpler than what I gave you up here. But it's not always so much about simplifying it. It's about finding an equivalent expression in which you can substitute, in this case, x, with whatever value the limit is. And it relies on a huge variety of things you've learned over the years in various pre-calculus math courses. So that's it. Let's look at these two examples. Same idea, evaluate the limit. Notice for this very first example here, if I substitute x with 4 right away, I get the square root of 4 minus 2 in the denominator, which is 2 minus 2, which is 0. So I get 0 in my denominator if I replace x with 4. So not surprisingly, that doesn't do me any good. I don't mind you checking, but don't expect it to do you any good. So what can I do here? Well, I got to find a way to rewrite this expression so that at some point I can replace x with 4. So what can I do here? Well, you always have a variety of ways. One thing is to realize is that this numerator is not a difference of squares, but I can kind of think of it as a difference of squares. And I can kind of factor the numerator into root x minus 2 and root x plus 2. Now again, if it was x squared minus 4, it's kind of a standard classic difference of squares, but it wasn't x squared. That's okay. It doesn't really matter as long as these two multiply together to make x. We're all good. And now notice if I do that, I can cancel out this factor of root x minus 2. And so that expression there is equivalent to just root x plus 2. And now at this point, there is literally nothing stopping me from just substituting x with 4. And so let's actually evaluate the limit. So now I'm going to write again the limit as x approaches 4. And I'm going to substitute x with 4. And you can see the answer, I'm sure. The square root of 4 plus 2 is 2 plus 2. So 4. I will say another option, because if you would have never thought of treating this like a difference of squares, okay, maybe now we can start thinking about it like that. But another option would be to multiply the top and bottom of this by the conjugate. Now if you ask yourself, what's the conjugate? Well, that's what I'm going to show you in the next question. So if I look here, I want to approach this by, at some point, using the conjugate. Although notice again, if I substitute x with 0 right away, it's clear I'm dividing by 0. That does me no good. But the conjugate is a binomial, so two terms, in which it's almost the exact same as this. But this term here, instead of being subtraction, is going to be adding. Allows us to take advantage of like a difference of squares in reverse. And so in this case, the conjugate would be root x plus 4 plus 2. And whatever I do to the numerator, I must do to the denominator. Chances are the last time you worked with the conjugate would have been in pre-calculus 12 with proving identities. Quite often, using the conjugate comes into play there. That said, what I'm going to get in a moment is not any simpler than what I have. Like I said, it's not always about simplifying this. It's about finding an equivalent expression in which I can evaluate, directly substitute, in this case, x was 0. So what's the point of this? Well, the numerator here, all I have to do is think, what is this times this, and what is this times this? The other two terms when I'm foiling out, I know will cancel each other out, which I'll say more about in a moment. But that's it. Root x plus 4 times root x plus 4 is x plus 4. Minus 2 times positive 2 is negative 4. And my denominator, I'm just going to leave it as x times all this mess. Why am I not distributing the x? Because I don't know yet if it's going to be of any use. That said, up here, notice I could have also gone root x plus 4 times 2, and then would have been minus 2 times root x plus 4. Those last two things would have just canceled each other out. And the whole point of multiplying by the conjugate is I know that's going to happen in advance. And so now notice, my numerator, my 4's cancel out. And so I have just x over x times this other factor. But not only that, my x's cancel out. So what I have is 1 over root x plus 4 plus 2. And now if you look at this, and you look at what I gave you right here, they are equivalent. I'm not sure if this one's so much simpler, but now I can just substitute x with 0, and I'm not dividing by 0, which means I can evaluate this limit, which means right here I'm going to now add in my limit as x approaches 0. And now it's a matter of just a little bit of arithmetic here. I get 1 over 2 plus 2, so 1/4. And so this idea of multiplying by the conjugate, which is what I showed there in blue, I could have applied right here. For example, this one, if I wanted to, I could have multiplied the top and bottom by root x plus 2. If I did that, and I FOILed this out, I would get almost the same steps as before. That's it. I'm trying to show you a variety of things. So through factoring, through using the conjugate, through finding common denominators, there's various approaches. The last example is kind of the messiest, but again, don't assume it has to take a ton of steps. I want to evaluate this limit. Notice if I replace x with 0, I'm dividing by 0, so that does me no good. So what can I do here? Well, I can use the conjugate again here. So again, if I multiply by the conjugate, it's always a binomial. So the conjugate only applies to the numerator because there's only one term down here. So if I want to find the conjugate, I want to multiply by the conjugate of the numerator, which in this case is going to be root 1 plus x plus root 1 minus x. Key is the exact same binomial as the numerator, just a different sign in the middle. My denominator, just do the exact same thing. If I don't do the exact same thing to my denominator, I've just changed the expression. It's no longer equivalent. Okay, looking at the numerator now, I know in the end all I really have to do is go this times this and this times this. If I FOIL it out, the other two steps will always cancel each other out. So I have root 1 plus x times root 1 plus x is just 1 plus x. Minus root 1 minus x times root 1 minus x is 1 minus x. All over, I'm just going to leave it like before, x times this mess. Sometimes a mess is not so bad. If I do distribute this x here, I don't think it's going to do me any good. If I do think at some point it's going to be helpful, then I'll do it. Until then, I'm going to be lazy and not do it. Okay, get rid of those brackets in the numerator. I have 1 plus x minus 1 plus x. So the ones cancel out. So to save myself a bit of time, I'm just going to write 2x in my denominator. Over again all of this. And again, I have a factor in my numerator and denominator of x. I can now cancel out quite nicely, which means now I can actually evaluate this limit because I'm no longer going to be dividing by 0 if I replace x with 0. So now I can actually evaluate limit as x approaches 0. Because notice at this point, if I replace x with 0, I'm never dividing by 0. Or any step before. If I look at all these steps before, and there's only 2 steps, but either this step or this step. If I substitute x with 0 in either of those steps, I would get a denominator of 0. I actually get a numerator of 0 as well. And so it just does me no good. And now I'll replace those x's with 0. It's a lovely number. So I can see this is going to equal 2 divided by 2, which is 1. And there's my limit. So the limit of all that was, in the end, equaling 1. And so right now, if you look at these few examples in our notes, for all the algebraic questions, involve the conjugate, or factoring, or finding common denominators. All things we've done before, just maybe not exactly like this, but all things we've done before, and there's also always more than one way. But these are things little tools you want to think back on if you're not sure how to approach something. Okay, but that's it for this lesson.